Welcome back to Eigrp concepts, the sequel. So in the previous video we left off at here where we have configured Eigrp on this topology. We added a new link that I've actually not assigned these IP addresses. So as in these IP addresses, you know that this topology is the one that we did subnet, from packet tracer and all that. So all I have done is for the one links, the /30s, we had .64.68 which we had used. Then so I've just taken .72/30. So this link will get .73, this will get .74, just so that we can explore some concepts and or terminologies that go with Eigrp. So in the previous video we left off where we were looking at during that Wireshark capture, where we saw Eigrp had several packets. So there is hello packet, and as you can see, hello packet forms neighbor relationships and also serves as a keep alive mechanism. So it is actually sent once every 5 seconds by default. 5 seconds by default. And you have what you call, is it a hold timer or dead timer? One of those. A dead timer of 15, meaning that if I miss the 3 hellos, if let's say if this is my R1 and then we have R2, so of course they're using the hello packet to discover each other. In that hello packet it will carry the parameters that need to match. Luckily for Eigrp, it's not a PK protocol compared to OSPF. It's not so choosy on its neighborhood. The main thing that mainly need to match is things like what do you call it, the process ID. If you choose process ID of 1, you have to stick with 1. So it discovers neighbors and also serves as a keep alive. So if I don't hear from you 3 times, because you can see if every 5 seconds you are sending a hello packet, if let's say you have something on the network, congestion, whatever, and a hello packet is sent, if I miss 3 hellos, it will bring down the neighbor relationship. So an update packets is I think some of these are a bit straightforward. So you have update query, reply, and ACK. So ACK is sent after every these 3 packets. If you send an update, you expect an ACK, because we said that Eigrp and OSPF, they don't use either TCP or UDP, and they don't use, that is at layer 4. At layer 4 they don't use TCP or UDP. They have their own reliability mechanism. That's why you have an ACK packet. At layer 3, another thing that you need to note is we talked about the various classes of IP addresses. So we have A, B, C, D. So D and E. So I said that in our networks we use A, B, C. D is usually multicast. Like you can see, Eigrp uses a multicast IP address of 224.0.0.10. Now RIP uses 224.0.0.9, and that is RIP version 2, because RIP version 1, and we don't even discuss that one because it's legacy. It's a classful routing protocol used broadcast. You don't want to broadcast a lot of broadcast communication in your network. At layer 4 for RIP uses UDP port 520. Now for Eigrp does not use either of these. It uses its own, I think it's called RTP And this is not to be confused with real-time protocol that is used with VoIP. Yeah, so it uses just some other, I think you might need to refer to the notes, but I think it's RTP or RTC. No, it's RTP. Port 88. Is it 88 or 89? I'm confusing. Either Eigrp or OSPF uses one of these, but I think Eigrp uses 88, OSPF uses 89. Okay, these are some of the stats that I'm just pouring here that that are just theories that probably will not apply that much, though if you are okay in the real world. Okay, what I'm trying to get at is most probably these things you need them for the exam, not for the real world. Though a possible scenario that comes to my mind for the real world is you know, if you're a firewall admin and you know, where you have a typical you know, we have been showing that, let's say you have a HQ router and a branch. We have been showing a simple link like this, but in reality we know that here probably you'll have a firewall, a firewall icon that we use looks like that, if I can draw. Yeah, so that gadget there is supposed to be a firewall. Yeah, the edge firewall that connects your network, the whole of your network back there. So for you to form a neighbor relationship with the branch, you might you know, not knowing those ports or the ports that you need to open, or all that might come to haunt you. But anyway, I think I've digressed. So those are some of the stats that you need to note for these routing protocols. For OSPF, it uses 224.0.0.5. OSPF have two. You have another one, 224.0.0.6. That is at layer 3. At layer 4, it doesn't use either TCP or UDP. It also uses its own reliability mechanism, and I think it uses port 89. Yeah, so I think I was just trying to explain what we saw in that Wireshark capture. And okay, dual algorithm stands for diffusing update algorithm. This is the algorithm that runs, or the engine that runs the Eigrp protocol. So, well, this is trying to explain. If you lose a network connection to, let's say router 2 loses connection to its LAN, it will send an update telling the neighbors, you know, because the work of routing protocols, of course, is to gossip what is going on in the network. So it will update the neighbors. The neighbors have to acknowledge, because these are is a reliable communication. Yeah, just like when you looked at TCP, we say that every packet that is sent is acknowledged. If you don't acknowledge it, then you have to resend, as in it's a reliability mechanism. There's a query packet that is sent, and it have to be, so the query, so now R2 is asking, hey, does anybody have a backup to this? Because router 2 doesn't know whether you know, whether maybe one of the routers is somehow connected to that downed network. So it sends a query, and the query have to be acknowledged. That packet have to be acknowledged. A reply, and the reply have to be acknowledged. So maybe in that case the reply was just a no. Yes. So even if they are not connected to 8, they still have to send a reply. A reply in this case will be no, and that packet have to be acknowledged. All right, we continue exploring the tables and terminologies that goes with Eigrp, so that we can understand the inner workings of Eigrp. because of the various things that can come to haunt you as you're doing your network maintenance and troubleshooting. So through the hello packet, we are able to discover neighbors, and we list them in the neighbor table. So in the previous video, we left off where we had configured Eigrp on all the routers. So the neighbor table, to see it and all of its glory, come to show IP Eigrp neighbors. So you see the neighbors with their ID. This is the neighbor ID, the interface where you go out of. So router 1 knows that it has this neighbor, and we'll need to go serial 0 that. So this is the hold timer. So it's actually called hold timer. OSPF calls it a dead timer. So we say that the hello whatever is sent in is sent once every 5 seconds. So if I keep on hitting up arrow, so you can see that this thing should never go below 10, right? You can see here is now 12. If I can do it fast, 13, because when we receive a hello packet, we reset. So you see it's not going below 10 because we said the hold timer is 15, and once every 5 seconds you're sending a hello packet. So in this case, because we are not missing, our network doesn't have congestion and all that, we're not missing hello packet. So so this stands for, I think, smooth round trip timer something. Anyway, those are stats to do with that protocol. So that's the neighbor table. So unlike RIP, that once every 30 seconds it floods the whole routing table, and so in the lab environment, that our routing table is no big deal, right? Show IP route. So the routing table here is no big deal because it's a relatively small routing table. If you do show IP route on a typical production network, in a big network, you'll see maybe like a full page or several pages of this routing table. So if every 30 seconds you're flooding the whole routing table to your neighbors, I mean, that's not very efficient. So advanced routing protocols like Eigrp and OSPF, they send a simple hello packet as a keep alive mechanism. And if there is a change on the network, there's always a triggered update, and I think we have seen those packets. So that's the neighbor table. Then we have the topology table. To see it and all of its glory, you can type show IP Eigrp topology, and so you can see this is the Eigrp topology table. It has some various terminologies that we'll need to understand. First of all, we have seen the update packets, the query, the reply, and all that. So we have passive and active. These are huge terms that I think we'll expound more in the next slides. So the routing table, this actually have nothing to do with Eigrp, as in the routing table is a router issue, is what makes a router. And so the way they are listed, of course, is the order into which the tables are formed, because once an Eigrp router discovers neighbor, it will go to the neighbor table. The neighbors will exchange the networks that they know. From there, you run a dual algorithm that will create the topology table. or rather all the updates are kept in the topology table. So from the topology table, you run the dual algorithm to choose the best route to get, and the best is put in the routing table. The routing table is always a table of the best routes. Yeah, and this is where things like administrative distance that we talked about come in handy. Administrative distance, I said, is the believability of a routing source. So in the topology table, you could have the best route, the backup route, the second best route. All the routes will be in the topology table. So the routing table will contain the best route, or the one with the least cost, yeah, with the least cost and the lowest administrative distance. Because if say you are running RIP, you're a crazy person that is running multiple routing protocols, or you have your own reasons why you're doing that. So maybe you're running RIP, you're running Eigrp. So router 1 is learning about, say, a remote network here, network X in question, yeah, from 2 routing port sources. So let's say you have RIP and Eigrp. So of course it will believe Eigrp because Eigrp have a lower administrative distance than RIP. And you as the network admin, you can even override all these routing protocols, where you come to the router and you say IP route whatever, you point it this way. Yeah, the router will believe you more because you have a higher administrative distance. And that's what we are seeing here. You can see that so D, first of all, so when you come back to the routing table, I know I'm jumping back and forth a lot, but I hope you can follow. So under the routing table, show IP route, yeah, so you can see under the codes we have D stands for dual algorithm, is for Eigrp. So this router is telling us that I know of this remote network, I learned it through Eigrp. So whenever you see, so unlike RIP and OSPF, where you see R, you know that it is RIP. OSPF, you'll see O, you know it is OSPF. Eigrp is D. This first number here is what you call administrative distance. This is the metric or the cost. So the administrative distance, if you remember, that of RIP was 120. So if I configure RIP on this one, we don't expect this thing to change. We'll still see dual. The routing table, because it contains the best route, will still believe Eigrp more. I think I've delved on that way too much. So about the terminologies, I said about passive and active. When you look at the topology table, yeah, the topology table show IP Eigrp topology, passive and active. So Eigrp is I said is one of the best, is arguably the best routing protocol in the world, were it not for the Achilles heel that it is Cisco proprietary. Some of the reasons for that is the only routing protocol that keeps backup routes, which of course will give us fast convergence. And by only, I mean is when you look at OSPF, you'll realize that OSPF also have a topology table. They call it a link state database, LSDB. Yeah, that is for OSPF. So it pretty much have the same backup, but the backup here, which I'm saying that is the only, as in Eigrp is the only routing protocol that keeps backup routes, is it has this concept of successor and feasible successor. As in, the backup route here is when you lose, say, the primary route, the backup route is put in the routing table instantaneously, meaning that you can have a sub-second convergence with Eigrp compared to OSPF in that regard, yeah, if you have a backup route, because OSPF, for it to choose the backup route to put it in the routing table, it will have to run the SPF algorithm. The SPF algorithm is quite CPU intensive, but this backup you're talking about is put in the routing table in a sub-second, whatever. Anyway, I think we'll see more on that as we expound more what you mean by successor and feasible successor routes. So why would you choose Eigrp? Or here I'm just trying to explain why I said that Eigrp is arguably the best routing protocol. It's because it's simple to configure, and this is where Cisco for some time it used to call it a hybrid routing protocol, because it borrows from the best from both worlds. As in, distance vector routing protocols generally are easy to configure, yeah. It has flexibility in summarization. This is a huge contrast when you look at something like OSPF. I think we briefly looked at summarization, where I said summarization is like the reverse of subnetting, and also summarization can be confused with supernetting, where I said that every supernetting is summarization, but not every every supernetting is summarization, but not every summarization is supernetting. I think I explained something like that in a previous video. So Eigrp is the only routing protocol in the world to do an equal cost load balancing, meaning that if say you have you know, like the network that we have in our GNS3, yeah, and let's say that these guys are actually combined, yeah. So let's say this is my R1. If, like, let's say this link here is 100 MB and this one is like is on a budget, it's just a backup link. You know, usually organizations will have a primary link that have higher bandwidth, but if that link goes down, they'll maybe have like a 50k link, yeah, 50k bps link, that's a backup link, yeah. So if this one falls, if this one fails or goes down, the work of a routing protocol, of course, is to make those automatic changes without you as the administrator. You know, if you had done static routes, which we have discouraged, your network can't automatically heal itself, yeah. So all the other routing protocols will, so long as the primary link is active, the one with the lowest cost, the one with the lowest metric, so long as it is active, all the traffic will be used on that link. This link will have zero activity, yeah. And you see there's a link that you're paying every month for, and that's not being used. So with Eigrp you can be able to, yeah, to configure it to do an equal cost load balancing. And I think this is what I said, combines the best of distance vector and all that. So let's go back to the tables and terminologies. So you have this feasible distance, and I think we see it when you do debugs, or is it in the topology table? So you can see about the successors. Okay, feasible distance, yeah, this FD stands for feasible distance, and is this one. So feasible distance is just the cost. So, you know, feasible means practical, yeah. Is it practical? Is it feasible to do whatever task? So feasible distance, this is the metric or the cost. So FD here is the least metric to reach a network in question. So like for instance, if you take this topology here, so let's say this network is the network in question, yeah, from the perspective of router 1. So router 1 is hearing about that network from both router 4 and router 3. So let's say the cost through router 3, let's say, is a major, it has higher bandwidth of say 100 MB. Though for one links, as in one wide area network connections, you'll rarely see guys with 100 MB connection, or unless it's some university or something. Usually guys have far less. Typical business environments, you'll find things like 20 MB, and maybe that's not a dedicated bandwidth, is but anyway, so let's say the cost there, the bandwidth is 100. Let's say for the LAN interface here is 1000. It's a gig link, yeah, it's a gig port. And let's say here we have 50, and let's say here is still a gig. So of course we can see the best path is this, because when Eigrp, it has this formula to calculate the metric where it factors in bandwidth and delay, yeah, bandwidth and delay of a link. And to see those, these are things that if you type show interface F00, we've been used to typing show IP interface brief, but to see the whole estate of a specific, to zoom in into one interface, you can type show interface F00 or whichever of these you want to check, yeah. So you can see the IP address that you assigned inside a notation. You can see the bandwidth. This is a gig. No, it's, so it have settled for, what is this? You need to divide this by 1024. So it have settled for, but anyway, so you can see some things like reliability, delay of the link. So when Eigrp is doing its metric calculation, it factors in those stats of a link, and I think we'll see how that metric is calculated. So back to the subject at hand. So we can see that it will of course choose router 3 as the best. So the feasible distance here, so let's say when you factor in the bandwidth and all that, you get a cost of say 10, and when you factor in, okay, 50 seems like a half of that, so let's say the cost then ends up being 100, a cost of 100, yeah. And is 100 all the way, as in all the way up to here, because of course there is a cost of this link and there is a cost of that. That's what you add up to become 100. There's a cost of say this link here and this link, that's what we are adding to get 10. Anyway, I think I should have said this is 20. It's not very logical that you have 100 as in 10 times worse when you factor in the bandwidth, but anyway, here we're just hypothetically speaking. So the least cost here being 10, that's what we call the feasible distance. Now advertised distance of course is the cost what your neighbor is advertising you, yeah, they're advertising to you. So like router 3 is telling, hey router 1, I know about 10.1.2.0 network and it will cost me this, it is this far from me, yeah. Of course there is always that when you factor in the bandwidth and delay of that link, there's a very small cost to it, yeah. So that will be what we call advertised distance. Advertised distance, or what at times they call reported distance. Now successor is the best route to the destination. So in this case, the successor route from R1 perspective is through R3. I think let me clear some of this gibberish and just retain the cost. So the cost here we had said all the way through, yeah, all the way to here is 10, and all the way to here, let's say, is 20. So the successor route is R3 and the feasible distance is 10. the reported distance here maybe let's say is 5. If it is 1,000 there, let's say also here is 5. Yeah. Now the feasible successor is what I was saying, a backup route is what you'll find in the topology table, as in the successor and the feasible successor is what you'll find in the topology table. So once you run the dual algorithm, the successor route will be chosen to go to the routing table. Now for you to qualify to be a backup or a feasible successor, a feasible successor is basically a backup. You have to meet the feasibility condition, which says to be considered a feasible successor, the advertised distance must be less than the feasible distance of the successor. If you read that a couple of times, you'll get confused. So what they mean by that is if your reported distance, in this case, we can see, you and I can obviously see that R4 is a backup. Yeah, if we choose R3 as the best route to reach the destination, R4 here we can see is a backup. But dual doesn't consider that as a backup, not unless it meets the feasibility condition. As in, that route will not go into the topology table if it doesn't meet the topology the feasibility condition. And that condition simply means that your advertised distance, in this case is 5, it have to be less than the feasible distance of the successor. The feasible distance of successor is 10, as in that's the least cost. That's the metric, the best metric to get to that network. So it is 10. We can obviously see that this is bigger than the reported distance of R4. Yeah. So if your reported distance is lesser than that, then you are a backup route. Maybe this can make a bit of sense if, say, let's say that you had another link that goes to another router here. This router have another whatever that comes, and so eventually you connect to this. Yeah. So you and I can obviously see that router 2 will also be a backup route, because if say this whatever's fail, they of course that one will be a backup. We can see that it's a backup, but probably that will not go into the topology table, or it will not be considered a feasible successor if, say, the reported distance, let's say that when you combine all these links, so let's say maybe this was 1,000, and you have some horrible links here that could be like 10 kbps, others are just a dial-up or whatever that is like horrible bandwidth. So when you combine the whole cost going this way, let's say maybe it came to something like 100, a cost of 100. So you see router 2 will have, when it is sending that update that, hey, I also know about that the network in question here, yeah, that I learned from my neighbors, and this is the cost to reach there, 100. So when router 1 is looking at that, it will see my feasible distance to reach that network is 10. So you're telling me that for you to reach that network, it will cost you 100. Yeah. So in this case, router 2 doesn't qualify, yeah, doesn't meet the feasibility condition to be called a feasible successor. So if my two links fail, of course router 1 will still choose router 2 as a backup, but in that case the dual algorithm have to run again, yeah, to discover that that actually is a backup route. So unlike the scenario here where, say, my router 3 went down, yeah, that primary link went down, this one will be will be put in the routing table instantaneously. You'll have like a sub-second convergence. Why we need that is Of course, nowadays we have real-time traffic when you talk of things like VoIP. So this is important in today's networks. You don't want you know, in some busy high-end companies, that subsequent convergence is important, because you might be having a CEO here of the company that is on a VoIP. Here I'm trying to draw an IP phone on a VoIP call, say to China here, and so if I can draw the VoIP, the IP phone with all that. So, you know, they were on a phone conversation, and they were about to seal a deal on whatnot. So the primary link goes down, and you know, before you reconnect, so this is where you'll have so anyway, this is where you'll have a disappointed boss here who you know, they'll tell you that they were about to seal a deal with all that. So anyway, we want a network that can converge in an instant. So I don't know whether I've made sense on those terms. Now, active and passive route, you don't want to see active when you look at your topology table. You come back to my topology, so you can see they are all P. P is passive. That's good. When you see them passive, it means that your network is stable, your network is converged. So active is where you are let me clear the gibberish, is where your routers are actively querying for a backup. So this is where, say, my router 1 had lost connection to its LAN, so it sends a query message. So before it can hear those updates, you'll see those routes marked as active, meaning that your network is still. So in fact, if you're doing a debug, you'll see that neighbor is possibly down or something like that. Yeah, in a small network, it's not a big deal, as in you'll get those replies in an instant. But when you have a network that, say, you know, have links going like, say, 30 routers, yeah, or 15 routers down the line, a huge network, it can stick inactive for quite some time. And at CCNP level, you can see how some of those in fact the term that is used is stuck inactive, yeah, SIA status. So in fact, you also don't want to see S, yeah, you don't want, this is a lesser you know, as in you don't want to see A, and S is bad. That's really bad. So but anyway, I think we have seen those terms. Now let's visit the not so friendly Eigrp neighborhood, because we have seen that forming neighbor relationship with Eigrp routers is no brainer, as in Eigrp is a good protocol to deploy, as in usually doesn't give you much issues, apart from things like this, the Kvalue or metric. In fact, when you're doing or when you're having issues with your Eigrp routers not forming neighborships, you might see messages like there is a Kvalue mismatch and all that. So what does Eigrp use to calculate the metric? Yeah, this number that we are seeing here is the cost. Yeah, these numbers, the feasible distance, and is the same one here. So like for instance, if we take this .96, we can see, so this is the feasible distance, meaning this is the best route to reach this this network. Is the lowest cost. Yeah, if we come to the topology table, just to prove that we first formed the topology table, so that then we go to the So you can see that network in question is this one here. It has one successor, and the feasible distance is this. This is the lowest cost, and you can see is this one here. So via dot 70. So in this case, dot 70. Who is dot 70? Dot 70. Router 3. Router 3. Where was I? Router 3. Router 3 is our successor. You can see is one successor, and this is the reported distance, meaning that router 3, so the network in question is this one. Router 3 have a reported distance of that. So now this is now the combined, yeah, from router 1's perspective. So if you factor in the router 3's reported distance to reach that network, the whole cost now all the way to, because router 1 have to factor in the cost of this thing, that's how you're getting 20 this here. So now to understand how we got there, the formula that it uses is it factors in all these we call them K values, yeah. So it factors in of course the huge ones are bandwidth and delay, and the reason for that is you can see the metric, the K value metric, whatever. You can see it's K1 times bandwidth plus K2. I think here is some. So you have load plus K3 times delay, K5 which is reliability, yeah, plus K4 and all that, and the bandwidth is the base is 10 to power 7. The delay is in microseconds. Anyway, the metric really boils down to this, because all these other values are zeroed out. So the only ones that are set is K1 and K3. The others are zeroed out. Okay, you can set them or you can turn them on, because you know, some admin might say, let's say if you have this my R1, yeah, and let's say that you have a backup route that somehow goes to, let's say that here we have the network X in question. So one might want to you know, to factor in some of these things, like you know, they say if let's say this is the best route, you're telling this router that you also factor in the loading, how the link is loaded, yeah. If it is too loaded, you then choose this as the best route. If the link is flapping, so if the link is flapping, this is where you'll see reliability going down, yeah. So when you look at the interface, you'll see so you can see the loading, the reliability. 255 out of 255, it means it's a stable link, it's not flapping, it's not going up and down. So you can factor in all those stuff to you know, although Cisco recommends not to interfere with those, because that will actually create an unstable network, yeah. Because when your users you know, maybe there's something that let's say is a breaking news, they all go to the internet, they want to check something, they load the primary link, that will affect the K value, whatever, and your router might now, you know, converge to this other link as the best. So anyway, just stick with the default. So if you stick with the default, if all these others are 0, the whatever just boils down to this. So the actual metric is 10 to power 7. You divide by the least bandwidth, and the cumulative delay, then you multiply by 256. Meaning that let's say if you have a topology that you know, you have a network there, then you have some backup link that goes like that. So let's say maybe here this is 100 MB, this is a poor link that have like 5 MB, and let's say this is 10 or something, say 50, and let's say 30. So of course, even looking at this, we can obviously see that this route will be the best, will be the successor route. Yeah. Now to calculate the metric, yeah, for this one, we'll take the least bandwidth. In this case is, and it have to be in kbps. So if it is MB, so we'll say 10 to the power 7, we divide by, let's say that these are kbps actually, so that we don't do the conversions. So we say plus, then you'll have checked the delays, yeah, the delays. So let's say 50 will have a lower delay of 20, this one maybe 40 because is you know, so we add the delay. So if it's 60, then you multiply by 256. So that's how you get these numbers that we are seeing, the metric. So of course it will compare that with if you are to do that, then you do 10 to the power 7 for this other link now, yeah, 10 to the power 7, you divide by the least here is 5, and let's say if you had a delay of let's say this is 10, a delay of 50 maybe, so you have plus 60 also. You do 256. So of course you can say after it is said and done, this will be a lower metric, yeah, the number that you get from here, because if the denominator is bigger, definitely your whatever will be smaller. All right, because if the denominator is this, eventually you'll get a big number here. The number that you'll get there is bigger compared to this, so here you'll get a lower number, and that's how you get the least metric. I think this is what I had tried to explain in terms of so we can actually see the protocol field is port 88. So I said 88, for OSPF is 89. So this is the generic Eigrp packet. You know that packet at the end of the day, that hello update packet is the one here, yeah. So it have to be encapsulated using the rules of the OSI model. So you have at layer 4, so this is where you'll find 88. At layer 3, that's where you'll find the multicast address of that, so at that header there. For the MAC addresses, we don't even care what are those. I think we mentioned about the network command. Yeah, so I think that's pretty much all about Eigrp. Only that we did not configure this backup link so that we can see the feasible successor in action. I think let's do that. Okay, I have configured the IP address. The IP address is here, which I think sorry. And my son have since joined the class. He's here keeping me company. So anyway, I've assigned the IP address on that link, and it's already advertised. You can see some neighbor whatever that were forming. I've also changed the router IDs, which for So I was just changing the router ID so that when you come, say you type show IP Eigrp neighbors, they're still showing as okay. In the lab environment, you can go to your routers and change the router ID to match the router names. That way, when you type show IP Eigrp neighbors, you can be able to see with those IP addresses that you can readily recognize. Or I missed, did I do a duplicate? Because I'm wondering why. Or there is a way we can do clear IP Eigrp neighbors. Let's down the neighbors. They form a neighbor relationship. I think you can put an asterisk. Neighbors what? Okay, let me down the all the neighbors. They have reformed the neighborship. Should be Eigrp. Still. Anyway, I think you have to do a shutdown. No, with IP version 6 you can be able to do that. So anyway, I think I'm digressing. I was just changing the router ID to yeah, for that. Anyway, I have assigned an IP address there and advertised it into Eigrp. So if I type show IP Eigrp topology, you can see that we have so if you take the network in question, this one, yeah, the network, the LAN of R3, so my router 1 is learning about it through router 2 and router 3, because we have since added this backup link. So it seems that my router 2 have met the feasibility condition, because you can see that here we have one successor who is router 2.70.70. No, who is my bad, who is router 3. So from here, of course, router 1 is saying that the best path for me to reach this network is router 3.70, and this is the feasible distance. I talked about the reported distance. So this one here is the feasible successor. You know, it's the feasible successor because router 1 is saying that I know that I can reach that network also through .66, and .66 you can obviously see is router 2. So this is the whole cost. So router 1 is saying that if I go through router 2, this is the whole cost, which you can see is higher than the successor route. So this is the reported distance. So we can see that router 2 met the feasibility condition because the reported distance here is lesser than the feasible distance. So we can see this 30 whatever is lesser than this, and that's how my router 1 is seeing router 2 is a feasible successor. Of course, we can go to the interface and mess with the bandwidth or delay. Like maybe we can add a delay, make a higher delay so that this does not meet a feasibility condition, and you know, it becomes it fails now to be a feasible successor. So because in an exam environment you might be given, say, an output, you know, they might give you a screenshot of an output like this, and then they are, you know, they phrase a question trying to see whether you know this will be the feasible successor. This is the total cost if you are to go through the feasible successor. and all that. So I don't know whether I'm making sense or I'm confusing you. So anyway, looking at the time, I think we have to put a break there. So anyway, let me know if I'm communicating. So with that, I hope this has been informative to you. I'd like to thank you for viewing.